Good morning, good afternoon, and good evening, everyone. Welcome back to another Rtds Technologies webinar. My name is Katie Sidwell. I'm on our technical marketing team here at Rtds, and I'm happy to be a host and moderator today. I'm here with my colleague Shane Jin, who will be giving a presentation and demo on our enhanced IEC 61850 sampled value streaming with the GTFPGA unit hardware. If you haven't been to one of our webinars before, go ahead and check out the interface. It's pretty straightforward. We will be taking questions through the Q&A widget throughout the webinar, so feel free to submit those anytime a question comes up, and we'll be answering them throughout the program. And then at the end of the demonstration, we will flesh out some of those questions live. And if you're watching this webinar on demand after the fact, keep in mind that you can still submit questions and you'll receive our responses in your email inbox. The chat window is not for your questions, but we'd love to hear from you. Introduce yourself, let us know where you're joining us from. It's great to see new and familiar names here in the attendee list. You'll find the slides for today's presentations in the handouts widget. And all of this will be made available after the webinar. So the recording, the slides, the Q&A document will all be sent to you in your email inbox if you registered for this webinar, and those should be available next week. All right, without further ado, I'm going to speak very briefly today. I won't be providing a general background on our technology, so if you're not familiar with real-time EMT simulation, I suggest you check out our website for some background information. I will focus on the difference between the GTNet card and our GTFPGA unit, which we're focusing on today. And then I'll pass the mic over to Shane, and he'll do a 15-minute presentation and then a really good 35-minute demonstration from the RSCAD software. And then we'll be happy to take your questions. The IEC 61850 standard is an increasingly important component of modern protection systems and thus of protection testing. The standard defines communication protocols for substation IEDs and provides an overview of the communication architecture for substation automation systems. Around 2010, Rtds Technologies released its GTNet capabilities, which was what first allowed users to incorporate IEC 61850 and 61850 compliant devices into the closed-loop testing process. Our protection and automation team participates quite actively in the industry working groups, such as the UCA International Users Group and IEC Technical Committee 57, which are focused on the 61850 standard. So changes to the standard itself, to standard compliant protection equipment, and to user requirements and use cases are what drives Rtds developments in the 61850 category. And we're really seeing an uptake of sampled values in commercial relays, and there's some precedent for it out there in substations now. So the enhancements we're discussing today are motivated by the fact that customers really need improved testing facilities for SV applications. This diagram shows a typical test interface for protective relays via IEC 61850 with the Rtds simulator. So in the gray box, we have a very simple simulated network, including sources, a line that can be faulted, circuit breakers, and instrument transformers. With conventional I/O, we would be bringing the voltage and current signals out of the simulation via analog output. But here it's done via IEC 61850 sampled values. In this particular case that we're exploring today, this is done via the GTFPGA unit. Those voltage and current quantities are sent out via the process bus and received by the relays. The relays can send their trip and reclose signals back to the simulated breakers via IEC 61850 goose messaging. And we don't have an FPGA-based option for goose messaging. That's done via our GTNet card, as you can see here. So we have GTFPGA-SV and GTNet Goose involved in this test setup. Of course, those digital signals, the breaker status and breaker commands, could also be sent via conventional digital I/O. So we have these two hardware solutions for IEC 61850 sampled value streaming to achieve this type of interface. And the first is shown here. It's the GTNet X2 card. So the GTNet allows the RTDS simulator to communicate with external devices over Ethernet, and it has a wide range of different communication protocols. So when you purchase the card, it includes the firmwares that are shown here. So beyond 61850, it also can run SCADA protocols like DNP3, synchrophaser protocols, Modbus, and generic TCP and UDP socket communication, for example. The card has 2 modules, and it can have 2 protocols operating simultaneously, one on each module. We have many users who use the GTNet card for sampled values streaming, and it can both publish and subscribe to sampled values. So each instance of the GTNet SV firmware can publish up to 2 sampled values streams with 24 channels each, or it can subscribe to a single sampled value stream. So the reason we developed a sampled values firmware for our GTFPGA unit is that the FPGA is good for offloading high calculation density applications from the main processing hardware, and it has really good control of timing, so it's an ideal way to implement a more capable sampled values firmware. Similarly to the GTNet card, the GTFPGA unit has its function defined by firmware, and there are multiple different firmwares available. So they're listed here on the slide. You'll notice that they're much more varied than the firmwares available for the GTNet, where the GTNet is more specifically for communication-based I/O. The GTFPGA unit is used for a wider range of applications. In addition to the sampled values firmware we're going to be discussing today, it can also be used to represent MMC valves and capacitor voltage balancing control for HVDC applications. It can be used to represent the small time step frequency dependent transmission line. It can be used for custom topology power electronic converter simulation at very small time steps. We call that our generic power electronic solver, or GPES. And finally, we have our sampled values firmware. In all of these different cases, the GTFPGA unit communicates with the central processing hardware via a fiber cable. And you can see here, the unit has 16 ports on the front that can be either fiber or copper-based Ethernet ports. And those are very key to the sampled values application. Shane will get into the details of what the FPGA-based sampled values firmware is capable of, but generally speaking, it can handle significantly more simultaneous published and subscribed SV streams than the GTNet card. So with the GTFPGA, you can simultaneously publish and subscribe up to 16 SV streams at the same time. It's also capable of higher sampling rates than the GTNet card. So the GTFPGA-SV component can operate not only in the main step environment, but also in the sub-step. So these time steps are much smaller, and we can achieve higher sampling rates on our data. Shane will give you a list of all the different sampling rates we can achieve. And he'll also get into the options for data and stream manipulation. This is a new feature for GTFPGA-SV only that allows the user to emulate delay, swapped packets, jitter, and other data and stream manipulations in order to identify vulnerabilities prior to deploying SV-compliant devices on the network. Commercially speaking, the acquisition cost of the GTNet X2 card and the GTFPGA unit are the same, so it's really up to what applications and requirements the customer is looking for. Finally, in the presentation and demo, you will see Shane talking about synchronization. And I just wanted to mention the hardware that makes that possible. It's called the GT Sync card. So this card synchronizes the RTDS simulator's time step to an external time reference, like a GPS clock. And it can accept several different external time reference inputs. In the demo, we are using IEEE 1588 PTP, but we're also capable of 1 PPS and iRig-B. And if an external reference isn't available, the GT Sync can actually provide its own time reference and act as a 1 PPS source. So this card is necessary if you're doing PMU testing with the RTDS simulator, and it's advantageous for SV output as well. Now I'll pass it over to Shane, and he'll give you some more details on the capabilities of the GTFPGA firmware, and he'll go through the demo.
Thank you, Katie. Hello, everyone. My name is Xinjing. I'm a protection automation engineer at Rtds. For this section, I will present IEC 61850 sampled value communication using Rtds simulator and GTFPGA. Protection and control systems nowadays, they are increasingly rely on critical measurements delivered through IEC 61850 or IEC 61869 sampled value. There are more and more commercial relays they are supporting SV protocols. SV is one of the most commonly used protection and automation protocol to interface the Rtds simulator with external IEDs. As more and more engineers are using SV for their protection and control purpose, we find non-genuine and non-ideal SV streams could cause protective relay misoperate, and further can cause serious damage to the power system equipment. The worst case, it can cause cascading failures in a wider power system area. So we need to identify the weakness and vulnerabilities of SV-based protection systems. This is the GTFPGA-SV hardware we are using. It has 16 fiber and copper Ethernet ports in the front. It is supporting 100 megabits per second or 1 gigabits per second bit rates. It can publish and subscribe up to 16 independent SV streams simultaneously and independently. This GTFPGA hardware can connect to the Rtds simulator using an optical fiber in the back of this box. Here is the typical connection of GTFPGA-SV. In the left, this is the Rtds simulator. You simulate your power system all in the simulator here. So the voltage and the current out of the secondary of CT and PD are sending to GTFPGA hardware. Within GTFPGA-SV, the voltage and the current will packed as SV packet and send out to the Ethernet. And the external IED will be able to subscribe the SV stream and retrieve the voltage and the current, and then go through their protection algorithms. In the other direction, the external IED can also publish SV to the network, and the GTFPGA-SV can subscribe the SV, and then feed all the information back to Rtds simulator here. So this is a fully two-way communication. Of course, all the devices in this setup here are synchronized to the same clock, use PTP, so that all the devices have a same time reference. This is all the sampling rates listed in the standards. The top two is the most common one because they are recommended by 9-2LE guideline. The highest sampling rate is 96K, which is recommended to use for high bandwidth DC control applications. All these sampling rates are supported by GTFPGA-SV. Here is the detailed capability of GTFPGA-SV. For lower sampling rates like those, we're supporting 16 outputs and 16 inputs simultaneously. And we're supporting up to 24 channels per streams. For higher sampling rate like 96 kHz, we're supporting 2 output and supporting maximum 24 channels per stream. And here we list another sampling rate, 250 kHz, which is not listed in the standard. Let's dig more of this 250 kHz. 250 kHz offers more than twice higher speed than 96K. It is required by HVDC protection and control applications. For example, for HVDC, traveling wave-based fault location, they usually sampled at 250 kHz to 1 MHz sampling rates. So that's why we're developing 250K here. The figure here shows a vendor's HVDC digital measurement systems. From the switchyard here, it can generate a SV using this high-speed merging unit. SV will feed back to the protective devices in this cubicle here. Similarly, using the GTFPGA-SV, it can also generate 250 kHz SV and send back to the protective relays inside those cabinets. And one GTFPGA-SV can replace 8 merging units for this scenario. Next, we talk about the subscriber features. The subscriber supporting parsing SCL file from the publisher. This way, it will automatically configure the GTFPGA, and it's much easier for the users. It also supporting filtering based on application ID and simulation flags. It also offering monitoring features. The SV can be monitored to show the packet intervals, and from there it can generate jitter stats like the right figure here. Also, it can give the detailed subscription status. For example, if you have an SV stream lost, one indicator will show in the runtime. If there's a CRC error, for example, then there will be a separate indicator in the runtime. The subscriber is supporting 2 modes. One is raw processing, the other one is interpolation. For raw modes, it will be like this. It's like stairs. For interpolation, since there's an interpolation at each time step, the waveform will be more smooth, like this. Here shows the difference between raw processing and interpolation. So for the last figure, you can see there's a stair-like waveforms. And on the right, the waveform will be much smooth compared to the left one. That's the difference between these 2 modes. Next, we talk about SV publisher manipulations. There are 2 types of manipulations. First is data manipulation. Here is a SV packet. Any segment or fields of this packet can be modified or manipulated on purpose, and the subscription relay will operate incorrectly. The second type is a stream manipulation. We know SV packet, they are traveling through Ethernet network from point A to point B. Ethernet network is dynamic and is changing all the time. For example, if the network is pretty busy, then it could cause noticeable delay in the subscriber. This represents the second type of manipulation. For data manipulation, the tool we provided support and manipulate all the gray segments in these figures. For example, you can change SMP count, you can change in time steps, you can change in synchronized status, and also you can change other parts like application ID. With a different change of the different fields, the receiving ID will react differently. We will see more details later on. The second type is the stream manipulation. Here we list the most popular 5 types of stream manipulation: stop and resume, duplicate, swap, delay, and jitter. Let's dig into more details. The first one is the stop and resume. It is quite straightforward. It is to simulate the loss of a packet on the network, which could happen in the real world. The second is a duplicate. In utility, in general, they have a redundant or parallel network design. If the parallel design is problematic, then it could happen that a duplicate package arrives in the subscriber. How the subscriber is going to react, that's what we're going to find out. The third one is a swap. Swap the order of two packets is to simulate a non-sequential arriving of packets due to problematic network routing. For example, packet A and packet B, they may have different network paths. When they arrive in the same destination, they may arrive out of order. How the subscription IED going to react? That's what we're going to find out. The fourth one is delay, which is pretty common. Is to simulate unwanted latency on the network. The last is jitter. Jitter is the variation of latency. It happens all the time in the network. We are able to add positive or negative jitter to the SV streams. We are able to control the jitter in the resolution of 10 nanoseconds, which is very accurate. This is due to the FPGA design, which can have a very good control of timing and clocks. We tested all the manipulation features on a commercial relay, and here's the results. First is data manipulation. We applied different types of data manipulation, and the IED react in 3 different ways. For example, if we change the destination MAC address, or VLAN ID, or application ID, then the IED will stop subscription. This makes sense and expected, because IED is constantly checking the destination MAC address, application ID, to make sure that the subscribed SV belongs to this particular IED. If any of those parameters changed or not match, the subscription will stop. The second type is, for example, if you change source MAC address, VLAN priority, reserved, and the relay will continue operating without any change. The third type will be more severe. It will affect the operation of the IED. For example, if you change the SMP count, the operation of the IED will be affected. Let's get more detail of this SMP count manipulation. Here we manipulate 3 SMP counts here. And the total sampling rate here is 80 samples per cycle. What we observed here is right after the SMP manipulation, there are half-cycle abnormal measurements here. What happened here is the SMP count manipulation, it corrupts the IED buffer. So when IED resampling, the correct IED buffer will generate incorrect values for the next half cycle. This is what happened. This is not expected, but this shows the value of GTFPGA-SV. You can do all the simulations in advance and find out those issues and address them in advance. We also test the stream manipulation on this particular IED. We applied latency of 2.5 milliseconds to the original SV stream. This IED operated normally. The IED's data buffer reduced the impact of the delay. Similarly, we also applied jitter to the SV stream. We applied Gaussian distributed jitter on the SV stream. The standard deviation is 2.5 milliseconds. We find that the IED also operated normally, and we believe the data buffer of this IED reduced the impact of the jitter. Of course, if you scale up the latency or jitter, at one point this relay will break. It will stop working properly. But we can find the threshold when exactly the IED will break, and that information is useful and important for engineers. Here's the summary of this presentation. GTFPGA unit combined with Rtds simulator allows for efficient and accurate testing of many SV-compliant devices. It supports up to 16 SV streams, publishing and subscribing simultaneously and independently. The GTFPGA-SV is suitable for ultra-high bandwidth applications, such as HVDC protection and control applications. Last, SV manipulation allows users to identify and address vulnerabilities in SV-based protection before the deployment on the grid. That concludes my presentation part. Next, I will switch to the demonstration to show all the features we have discussed. For this section, we will demonstrate 4 demonstration examples. The first one is publisher, the second one is the subscriber, the third one is manipulation, the last one is the full capability of GTFPGA-SV, including 16 publisher and 16 subscriber at the same time. First, let's check out the publisher. Now I'm in RSCAD FX software. This is a simple GTFPGA-SV publisher case. They mainly including 3 parts: GT-Sync, GTFPGA-SV component, and all the output signals that are required for GTFPGA-SV. For the GT-Sync component, you can find under Protection Automation, Synchrophasers, and then you can drag the GT-Sync component into your draft case. The next is the GTFPGA-SV component, which is the key of this demo. This component you can find under Protection Automation, IEC 61850, and it's over there. And then you can drag the component from there into your draft case. If you open the component, you will see all the settings for it. The first tab is Configuration, which including all the high-level overall settings for this component. The most important ones are number of output SVs. We just choose 1 for this demonstration. The next one is the number of input SVs. Here we set to 0 because we focus on publisher for now. And next you can specify your system frequency between 50 or 60 Hz. Another important parameter is this one, GTIO fiber port number. This is the port number that you connect in your GTFPGA box into your NovaCore or PB5-based system. The second tab is Output Configuration. Under this tab, you can connect in all the GT-Sync signals to your GTFPGA so that the timestamp from the GT-Sync can be included into the published SV streams. The third tab is Output Manipulation, which we disabled for now. The next tab is the Output Configuration for port 1. This tab including all the important parameters needed for the SV published streams. So the first one is the sampling rate, which we discussed in our presentation. We support all the sampling rates listed in the standard. We're also supporting 250 kHz for high bandwidth applications. Next, you can specify IED name, application ID, VLAN over there. The next is the multicast address, which is very important. Here's the higher 3 hex number. Here's the lower 3 hex number. You can also choose to include refresh time and the SMP simp in your message. If you choose CC, that means the value of that particular field will be controlled using an external signal. Same thing for the simulation flag. And next is configuration revision. The next is all the settings for the channels included in the SV stream. First, you can specify the units for the signals you are feeding, either kilovolt or volt. The next, you can choose how many voltage and current channels included in your SV stream, from 1 to up to 48 channels. The next 5 parameters are used to specify the details for channel 1. For example, you can choose either it's a float or integer. You can specify it's a A-phase current, B-phase current, or voltage, etc. Here you put the signal name for this particular channel. Next, you can offset or scaling of these channel values. Same thing for the rest 23 channels. After you specify all the 24 channels, you can scroll down to the bottom of this tab, where you can specify the qualities of the SV stream. You can choose either word or use bit style to control it. Here we choose a word, and then we specify this control signal to control all the quality bits. Once you're ready, you can click OK. Next, let's check all the output signals required for GTFPGA-SV. Inside this hierarchy box, there are another 4 hierarchy boxes. The first one is for source, to give the voltage and current for different channels. The second is all the channel specifications. The third one is qualities. The last one is for simulation flag and the synchronized values. Let's check the first one, source. This is just some simple circuit to generate some dummy voltage and current. The second one is channel specification. You feed those voltage and current into the channel you want, from channel 1 to all the way channel 24. The third one is quality. You can control the quality, either use bit style like this, or use the word like this, which we are using this one for now. The last one is the simulation flag and the synchronized status. We can use some simple switch or dial to control those signals. That is all the output signals required for GTFPGA-SV publisher. Now let's switch to runtime. This is the runtime of the draft case. We have some source control, some simulation flag control, some SMP sync control, and quality word control. On the right is the Wireshark capture of the SV streams. Let's run the case. You can see the real-time SV packet published into the network from GTFPGA-SV. Let's examine the packet. Right now, for the publisher, the sim flag setting is to all 0. Simulation flag is corresponding to the highest bit of reserved 1. So right now it's 0 as well. If we set to 1, you will find that the highest bit of reserve 1 is also set to 1. If we set it back, of course it will change it back. Next, we can change the value for synchronized status. Right now is 2, which is corresponding to the value here. SMP sync is 2. If we change it to 1, for example, and it will also update in Wireshark as the same value. Next, we can check the quality bits. Quality is corresponding to here. Currently, it's all 0. If we can toggle it, let's check it. It will also update to the value you set it in your runtime. That concludes the publisher demonstration. The next is a subscriber demonstration. This is a simple subscriber case. It is built based on the previous publisher case. There are some extra components we added here. There are filter input here, and also we add a Unix Converter over there. We will come back to those later. First, let's check out what the change to the GTFPGA-SV component. You notice the graphic difference compared to the publisher only. Right now there's input, also has output. In the configuration here, we can see we specified two outputs for port 1 and port 2. We also specify one input for port 1. What we eventually want to achieve is like this. We want to use port 1 to subscribe the SV stream published from port number 2. The SV stream published for port number 1 will be simply ignored. Let's open the component. You'll also notice there are some extra tabs. First, you can see there are two outputs right now corresponding to the port 1 and port 2 publisher. There are also input configuration for port number 1. Besides, there is an input configuration for all the 16 ports. Let's go back to the input configuration. The first one is sampling rate, which you need to match it with the publisher. Here we choose the port 2 as our publisher, which is 80 samples per cycle. We set the same. The next is expected number of voltage and current. We set to the same 24 channels, same as publisher. Here you can use SCL file for configuration of your subscriber, or you can choose manually put the multicast address into the field. You need to make sure that the MAC address is matching with your publisher. The next is the filtering parameters. The first one is application identifier filter. You can choose to enable or disable in runtime, use an external control signal. And this is the actual application ID filter values you want to use it for your filtering. Similarly, you can use it for simulation flag. And this signal, it is to indicating the user that if there is a new packet coming into the subscriber. If there is, it will be high as 1. If not, it will be 0. Next is the value of the simulation flag in the subscribed SV packet. And the next is the total number of ASDU, SMP count value, configuration revision, SMP sync value, ASDU index, and the total actual number of channels in the SV streams, because sometimes the actual number could be different from the expected number setting at the beginning, as here. The component can also give the time step inside the SV packet. The first one is the second part. The second one is the nanosecond part. As we discussed in the presentation, the subscriber supporting packet interval, which from there you will be able to generate the jitter stats. It can also give the subscription status in real time, such as stream lost, CRC error, etc. For the rest of the session, all those parameters are used to configure all the channels, similar to the publisher, including the units, date format, date type, the signal name, and the quality name, as well as offset and scale factor. There are settings for all the 24 channels. And that's all the settings for the GTFPGA-SV component. Once you're ready, you can click OK. Next, let's check other parts. The output signal is the same as publisher. The filter input is used for generate those 4 signals used in the port 1 subscription. First one is for application ID enable or disable filter, and the next is the actual application ID filter value used for filtering. Similarly for the simulation flag and the simulation flag value. The last component is the Unix Converter, which you can find it in the library. you can type Unix and hit enter. You will be able to find it. This component can convert the timestamps retrieved in the SV subscriber and convert it into a human-readable time, such as year, month, day, hour, minutes, etc. Now we can compile the case and go to the runtime. Now we are in runtime. The left side is all the control signals for output. On the right side is all the subscribed signals from the SV stream. Let's run the case. Now the case is running. First, let's check that the input is matching with the output. Let's update the plot here. First of all, let's check the simulation flag. Currently, for port 2, we are setting to 0, and in the input, we find the same value. Now we change the simulation flag to 1 for port number 2. The subscriber will also update to 1. If we change it back, it will update at the same time. Similarly, for SMP sync currently is 2, and the subscriber shows 2 as well. And if we toggle it to a different value, it will update accordingly. Let's check this plot. The first one is the publisher and the subscriber channel. We can see that the publisher and the subscriber, they are matching perfectly. The second one is packet interval, which gives the interval between two packets in real time. The next one is SMP count. They are continuous without interruption. The next one is ASDU index. It's constantly equal to 1 because we are choosing the 9-2 LE sampling rate. There's only one ASDU in total. On the right, we saw there are 3 lights. The first one is a new packet indicator. As long as there are new packets, the light will on. The second and the third one is the status signal to indicating the subscription status in real time. If there's any error, the light will be on. Right now, everything is good, so there's no error indication at all. The next, you can see the number of ASDU equal to 1 as expected. And you can also check the configuration revision that should match with your setting in your publisher. And also we can find the number of channels is 24 channels. And also we can retrieve the timestamp inside the SV. We can find that is the accurate and meaningful time. Next, we can check all the 24 channels we have. And we pull in the data from NovaCore. You can see here, publisher and subscriber, they are matching perfectly. If we apply some change, and let's see what's going to happen. You will notice that the publisher and the subscriber, they will update at the same time. So you can see any change in the publisher will be truly reflected in the subscriber. We can also check the qualities. The quality currently is all 0 for all the 24 channels. If we change it in the publisher, you will find the subscriber will update accordingly. And that concludes the second part of the demonstration for subscriber. Next part is manipulation demonstration. This is a manipulation case. It is built on the previous subscriber case. The manipulation part is added here. Also, the component of GTFPGA-SV is also modified. Under the Output Manipulation tab, for port number 2, instead of disable, right now it's enabled. So you can manipulate VLAN priority, VLAN ID with external control signals. Same thing for application ID, length, reserve 1, reserve 2, and number of ASTU, configuration revision. Also, you can manipulate SMP count with a trigger. You can also manipulate destination MAC address, source MAC address. Next is the stream manipulation part. The stream manipulation supporting 5 modes as we discussed it in the presentation. 0 for stop, 1 for duplicate, 2 for swap, 3 for delay, 4 for jitter. Simply put the manipulation you want over there. We can start from 0, which is stop and resume stream manipulation. And these are the control signals that to use to real-time control your stream manipulation. Under stop mode, you can use external signals to control when you want to stop or resume your publishing. Under duplicate mode, you can use external signals to control when to duplicate or when to stop duplicate. Same thing for swap. If you choose delay stream manipulation, you can set your delay over there. And the control signal here can use to control when to apply the delay and when to remove the delay. If you choose jitter stream manipulation, you can apply your jitter with these external values. That's all the settings for manipulation. If you're ready, hit OK. The next, let's check out all the signals required for manipulation. There are 2 hierarchy boxes here. One is for data manipulation, the other one is for stream manipulation. Let's check the first one. The data manipulation gave the control signals for different segments of an SV packet, such as source MAC address, destination MAC address, VLAN priority, etc. The stream manipulation gave all the control signals for the 5 different stream manipulation modes: stop, duplicate, swap, delay, and jitter. That's everything for this draft case. Now we can go to runtime. This is the runtime for manipulation. It's very similar to the previous subscriber case. On the bottom here, we add all the manipulation part. Let's run the case. On the right side is Wireshark to capture the real-time SV stream. Here you can see there are 2 streams in the network. One have a MAC address as 040100, which is from port number 1. There's another one with 040101. It's from port number 2, which is our focus. Let's apply some manipulations. First, we can change the source MAC address. Currently, it's 70B3D5 54265A, which is matching what we are seeing in Wireshark. We can change the value of those, which is 5F right now. You can see that the value is also updated in Wireshark. We can change it back. You find in Wireshark they also change it back. We can also change the destination MAC address. So currently it's 040101. We can change it to a different value, say 07. You can see it's also changed in Wireshark. We can change it back. Here in Wireshark, we can just focus on the stream out of port number 1. You can do this. Right-click, apply as filter, choose selected. Then it will only show you the streams with the SV destination of 0101. We can manipulate application ID here. Currently it's 4002, which is the same showing in Wireshark. If we change it to some other value, like 4007, for example, it will also change. Let's change it back. You can also change the length of the SV packet. Currently is FA, which is corresponding to this value, 250 in decimal, which is FA in hex. We can change it to, say, FB. Then it will also update it over there. This is a length field. Next, we can also change the reserve 1 and reserve 2. Currently, they're both 0, which is matching what we have here. If we change it to some other value, they're also updating over there. We can change them back. Next, we can manipulate number of ASDUs. The number of ASDU is 1, which we can see here, as well as in Wireshark. We can manually manipulate whatever values you prefer, for example 5. You can notice that in a subscriber, this value is also updated, and in Wireshark, you can verify it as well. Next, we can manipulate the SMP count. We can maximize this window first. So this is the trigger signal to apply SMP count manipulation. You notice that as soon as apply SMP count manipulation, the subscriber will mess up. You can stop SMP count manipulation. So this is all the data manipulation we can apply using GTFPGA-SV. Next, we can focus on stream manipulation. Currently, the stream manipulation mode is set to 0, which is stop and resume. We can apply stop manipulation by toggling this switch. You notice that the new package indicator is gone, and the subscription status is light up. That means the SV stream is lost. We can change it back by toggling this switch again. Now you can see the subscription is success again. The error ID is turned off. We can also apply other 4 types of stream manipulation. We can go back to the draft case. We can set this value to others, like number 1, duplicate. Okay, compile. Now let's restart the case. If I apply duplicate, in the Wireshark, you will notice the difference. So for this packet, the SMP count is 2886. The next one is also 2886 because that's the duplicate out of the manipulation. Same thing for the following packets. If we stop duplicate, let's capture it again. It will go back to normal without duplication. This is the duplicate manipulation. Next, we can apply the delay manipulation. Which is number 3. We can rerun the case. By toggling this switch here, the delay will be applied on the published SV stream. We can zoom in. You can see the delay right over there. By changing it back, the delay will disappear. That is the delay manipulation. Next, we can check the jitter manipulation. Here, by changing the stream manipulation to number 4. We can rerun the case. Now we are applying Gaussian distributed jitter on the SV stream. Pay attention to the packet interval in the bottom corner. Now we will multiply the jitters to 10 times. The packet interval will be also 10 times worse. That concludes the manipulation part of this demonstration. The last one is the full capability demonstration of GTFPGA-SV with 16 publisher and 16 subscriber at the same time. This is the 16 output, 16 input case. Let's check the component. Here you can see that the number of output is set to 16, same for the number of inputs. You can also find the tabs for each output and input. Eventually, what we want to achieve is output 2 connecting to input 1, output 3 connect to input 2, and similarly for output 16 to input 15, and output 1 to input 16. Now let's compile the case. Let's go to Runtime. Now we can start the case. You can see that all the 16 ports, they are subscribing properly. And there are no errors for stream lost or CRC error. If we update this plot, you will find the publisher and the subscriber is matching perfectly for all the 16 ports. That finished the 16 publisher, 16 subscriber demonstration. That's the end of demonstration. Thank you for joining us.
Okay, thank you everyone for joining us today. I'm going to lead our question and answer session here. Shane, can you just test your audio, please, to see if we can hear you?
Hey, everyone. Hey, Kristen, can you hear me now?
Yes, I can hear you. Thank you. Okay.
Is it clear?
Can you hear me?
Yeah, it's very good.
Okay, good. I have some questions here that I'd like you to answer. The first one is, we had someone ask about whether we can publish and subscribe the Goose messages with the GTFPGA unit and whether there are any plans for that. Can you talk a little bit about that, please?
Yeah, internally we have discussed this several times because for the SV we develop, we receive a lot of very good positive feedback. And also several engineers, they are asking if we can add the Goose capability on top of the SV. So definitely, yes, it's under the considering right now. It's just based on the priority, or how to fit our current project or schedules. Yeah, definitely, yes. And one more point is lately we are focusing on GTNet Goose. And the GTNet Goose version 7, which is the latest one, it's much powerful than before. And I think we did a webinar similar to this one a month ago. And from there, all the experience we learned on GTNet, we possibly can migrate to GTFPGA so that we will have a very powerful tool for the user to use. Yeah. Also, if users are interested in the latest Goose capability, yeah, I highly suggest you can try the GTNet Goose version 7 and also check out the webinar and from last month. It will be very useful. Yeah.
Okay, great. Thanks for that, Shane. The next question, we had someone ask about the sim flag parameter and how to use it. Shane, can you touch on that?
Yeah. Simulation flag is quite useful, and all the behavior under a simulation flag is defined clearly in the standard. The main purpose for simulation flag is, for example, for testing. When we're testing, for example, some relays in the on-site, and we want to make sure the relay working properly, but we don't really want to trip the breaker, right? So it's just for testing or commissioning. So we use this simulation flag as an indicator. If the subscriber receiving on SV with the simulation flag as a high or activated, then the SV receiving device will know that, okay, this is a simulation, it's a testing. I can check all the functions of my relay, but I won't need able to actually generate a trip signal to actually open the breaker. So that's the purpose for simulation, which is quite important for all the testing engineers and the protection engineers. Yeah.
Can you hear me now?
Yes.
I can hear you, Katie.
Excellent. Okay. I apologize for that. Some technical difficulties on my end. I will jump back in here. Thank you so much, Christine. Okay, Shane, we had a couple of questions about delay. Someone noticed the offset between the publisher and subscriber sine waves in the demonstration. So do you maybe want to talk about the delay a little bit and the delay setting as well?
Yeah. Delay is quite important. And it's for some testing or for some standard, and the delay specification is strictly, clearly and specified, so that all the protection or all the control applications, they can work in properly. For the tools we developed, we can very accurately control the delay of the publisher we developed. The delay we supporting for manipulation, the range is between 0 to 3,000 microsecond or 3 millisecond. And as one of the user, I think it's Charles, asked that it's could possible that we can increase 3 milliseconds to even larger, because that could happen in the real world, correct? And the reason we set to 3 milliseconds is because the onboard buffer on the FPGA, and we have to buffering all the packet on FPGA during those either 3 milliseconds or 2 milliseconds delay manipulation. So that's the limiting factor over there, why we're setting to 3 milliseconds. But it's possible that as we optimize the design of the, for future, we possible can expand the size of the buffer so that we can increase that parameter for users' application. Yeah. So yeah, we can do that in the future. And also the accuracy of the delay we can control is in the resolution of 1 microsecond, which is very, very accurate. It's also because of the FPGA design. So we have very precise control on the clocks and the timing. So yeah, and also just to be aware that the delay we are talking about here is all the delay we can control on the hardware we have, which is GTFPGA. As soon as the SV stream go out to the network, the delay generated on the network is not controllable, right? It's totally up to the network condition. If the network is congested or very busy, then the subscriber will also have a varied delay. And that's a separate factor. I just want to point out that all the delay we can control is our own hardware. The network condition, you cannot control those. Yeah.
Excellent. Thank you, Shane. That's super clear. We had a question about the XCBR capabilities in our new Goose component, which runs on the GTNet. I believe that's the switchgear specific logical node. So do you want to talk a little bit about those capabilities? And there was also a follow-up question about whether all 512 logical nodes are in one single IED.
Okay, yeah. The question is a good question. Yeah, XCBR is one of the logical nodes defined in IEC 68050 standard in Chapter 7. It is designed to modeling the switchgear circuit breaker. So currently, each XCBR node is supporting as 32 position. So technically, you can control 32 devices. That is not changed, which is the same as older version Goose firmware. What we upgrade or we increased is the total number of logic nodes. For example, before for Goose version 6, we're supporting up to 64 logic nodes, right? But right now, and we can supporting up to 512 logic nodes. You can choose whichever logic nodes you want in your either one IED or multiple IED. It's just based on your configuration. It's very flexible. The new tool we designed is called ICT, IED configuration editor. From there, then you can configure either one IED or two IED or whichever you like. But the limit, the total logic nodes limit for one GTNet card, one module, is 512 logic nodes. One GTNet X2 card has 2 modules, so basically you can have 1024 logic nodes maximum for one GTNet X2 cards. Yeah.
Excellent. Thank you, Shane. I believe that wraps up our questions. So I want to thank everyone so much for your attention. I do want to plug a couple of upcoming events we have. Our next webinar is going to be on Wednesday, November 3rd, and it is going to be with Dr. Ali Dekordi, our machine modeling specialist, and there will be an emphasis on polyphase machines for renewable energy and naval applications. So that should be really interesting. And also later in November, we are kicking off our User Spotlight Series 2.0 event. So you might be familiar with this virtual event series we did last year. We are focusing on customer applications of the Rtds simulator and featuring them in short presentations. And we're going to be doing one User Spotlight Series event every 2 months for quite a while. So please head to our website and you can search for User Spotlight if you're interested in the event. And we'd love to receive some more abstracts for that event too. So pass that information on to your colleagues. All right. Thank you so much, everyone, again for joining us, and Shane for the great presentation and question period. And I hope everyone has a great day.
Thank you. Thank you, everyone.